Hi, my name is Nathan Ong. I am a fourth year PhD student in the biomedical sciences program studying paleontology. We're actually over here at the Tulsa campus currently. And today I'm going to be discussing one of the chapters in my dissertation. This is sort of the preliminary, it started out as preliminary data, but has since ballooned into being sort of a full-blown occurrence-based study and probably worth its own chapter. Um, the name of the project is using shell ornamentation to document Pan-Trionychid turtle diversity and distribution across the KPG boundary. So Pan-Trionychids are soft-shell turtles, and they have these little bumps and ridges on the outside of their shell, and some of them go extinct at the end of the Cretaceous, and some of them do not. And I was wondering if you were to use the data of this ornamentation morphology, if you were to count up those occurrences, if that would more or less align with the macro anatomical data sets that are already fairly well established. So with that in mind, I'm just going to go ahead and kind of walk you through very briefly what this project is about. Let's see here. So the Maastrichtian is the very end of the Cretaceous. The Danian is the very beginning of the Paleocene, and right in the middle is where the asteroid comes down and knocks out, about what is it, 70 to 75% of land animals. The rock record from this time is kind of tricky because you have a change in the rocks from that time, what's called lithofacies change. So primarily, we know the end of the Maastrichtian, the age of dinosaurs, from the Hell Creek, and then we know the time right after from the Fort Union Formation and the Tolic member of the Fort Union Formation. But because there's this marine transgression that's going on at the same time of the Cannonball Seaway, you have a change in lithofacies across the boundary. And so you get a few formations like the Nacimiento Formation, the North Horn Formation, and the Denver Formation that straddle the boundary. But by and large, the vast majority of fossils that we know of come from the Hell Creek and Fort Union formations, which don't have a whole lot of lithofacies overlap across the boundary. There are a few places that I've tried to, sort of qualitatively denote here, where the Hell Creek will poke up into the Paleocene, and a few places where the Tolic will, dip down into the late Cretaceous. But by and large, the vast majority of specimens are going to come from one or the other. And the reason I'm telling you this is because it ends up being a pretty major problem in this dissertation because it's hard to say if the changes across the boundary are because of changes in the formation or changes in the actual, anatomy, abundance, and ecology of these animals. So just keep that in mind as we're going through this project. It'll come up more and more. We have quite a lot of different groups that we are studying. So the soft-shell turtles are mostly derived by the Trionychids and the Pan-Trionychids. All of these guys in the kind of teal are your semi-terrestrial or semi-aquatic specimens that are really very classic soft-shell turtles that you expect to see. Whereas Basilemys is like a classic terrestrial, tortoise-like turtle. And then Adochus is like almost exclusively aquatic, or at least this is sort of how we tend to think of them as being. There are some other animals that would occasionally come up in as identifiable specimens. Neuronchilus is a very large terrestrial turtle. Eubana is just sort of a stand-in for all the banans generally. Chelydrids are snapping turtles, and their canon, they of course are alive today. Hoplochelys is a close relative. And then interestingly, Compsomys is actually a paracryptodyryn. So, turtles have either cryptodyrans or pleurodyrans, depending on how they put their neck into their shell or kind of tuck it to the side. And Compsomys is some of the most primitive turtle that is, in this fossil assemblage. But interestingly, it has an ornamentation morphology that is very distinct and very easy to identify. And so I wanted to go ahead and see if it was doing anything interesting in the data set. So basically what I did was, we can move this guy. I went to 8 different museums. I called it Turk Tour, and I did that as sort of one big road trip that I undertook in August of 2021. where I went to eight different museums and I took about 2,000 photos. Um, and then I sort of put together an ID guide based on the ornamentation that other people who know more than I do have identified. Um, and the thing about identifying ornamentation is that there's some specimens or there's some taxa where it's very clear, like this is absolutely 100% Compsommes or Halopanoplia distincta or Plastomenace. But then there's others like Aspideratoids versus Aspiderites versus Axostemes versus Atopasemes that are, for whatever reason, they just have a lot of overlap with their ornamentation. And so even though I'm referring to these taxa here, I would advise that you sort of think of them as being more like almost like akin to ichnotaxa, where there's clearly a biological relationship to these patterns, but it's maybe not one-to-one per genus. And so I'm more talking about the ornamentation itself as opposed to the absolute abundance of these taxa. So just keep that in mind as we're going forward. I was able to identify 958 specimens, and there are more along the way coming from UCMP's collection, Berkeley. I also took the latitude and the geologic age gathered from associated specimen data. So they'll say, here's X locality, it's X in age, and it was at X latitude. I also had to do some lithological context and in situ, or figuring out if specimens were in situ or not. So there's this region called the Bug Creek area where it seems like these large rivers were essentially going through and bioturbating all these specimens. So what looks like something that's Quercus, post-extinction, just from the bioassemblage, actually turns out to be Maastrichtian before the extinction that just got reworked by a river at some point. So I had to go through the field notes and sort of manually determine if those were Maastrichtian or Danian deposits that were in situ or not. And then finally, I took all that data and I analyzed it in R and I produced the figures in R. And then I actually had to also produce some of the figures in Google Sheets. It's kind of janky, but unfortunately, just for whatever reason, Google Sheets or R does not like doing pie charts. Speaking of pie charts, these are all made from Google Docs. As you can see, the vast majority of specimens are coming from the Maastrichtian, about 2/3 or so. And of those, 96% of them are coming from the Hell Creek Formation. And that is a big part due to just a heavy amount of sampling from the Hell Creek project. But you have a little bit from, Laramie, Nacimiento, North Horn, all that stuff. Danian formations, again, are much more variable. So the vast majority are coming from the Tulloch Formation, and by extension, Fort Union could be lumped in here. But you also get North Horn, Denver, Nacimiento, Dawson, some of those guys. So in terms of the alpha taxonomic assemblage, that's basically what genera are there, with a few that I, higher order stuff like Trionychidae that I wasn't able to take out of the data set. And these are based on the in situ, or what I infer to be the in situ ages of these specimens. And generally, you'll see that there's not a whole lot of difference of relative abundance across the boundary. Aspideratoids is 18.5% in the Maastrichtian assemblage and 17% in the Danian assemblage. So, cool, not that big of a difference. One of the interesting things that I think is worth noting is that Compsommes, that Paracryptodiron, jumps from about 10% relative abundance all the way up to 19.5% relative abundance, which I find really interesting. But everything else is more or less what you'd expect. Other authors have pretty consistently said that Halopanoplia goes extinct at the boundary. I saw, at least from my ornamentation data, that it still makes up a pretty significant assemblage, which to me says that there's something there that has ornamentation that is consistent with Halopanoplia, but I'm not going to go ahead and say that Halopanoplia actually survived the extinction without more of that macroanatomical data set that other workers are working on. So take that with a slight grain of salt, but everything else is more or less applicable. Latitude distribution was interesting. You'll see In green is your Maastrichtian data, and in orange is your Danian data. And there's just a lot more of your Maastrichtian data points from different localities. And then Danian has a much wider range, but I think more than anything, that's just due to the differences in how the formations are geologically spaced out. That being said, even when you look at just the difference between the Maastrichtian Hell Creek Formation and the Danian Tulloch Formation, which are right on top of each other and right in the same places, you do get a few consistent trends. So here I've taken that latitude distribution, I've split it up by taxa, and then I've also split it up by age. And the general pattern here is that you'll have something that is at a very, very high and consistent latitude in the Maastrichtian deposits, and then in the Danian deposits, you have a much more variable latitude and generally lower latitude. So, if I were just looking at, across all the formations, then I think some of that variance could be explained by a good chunk of that variance could be explained by just differences in the geographic position of, Nacimiento, Denver, Fort Union, all that, as opposed to Hell Creek. But this is mostly looking at your Maastrichtian Danian deposits of Hell Creek and Tulloch, respectively. So to me, what that says is that even once you take out your taphonomic differences, you still have a pretty significant signal in terms of your latitude distribution going down and becoming more variable. So if we were to actually statistically test some of this stuff, one question was, does the alpha taxonomic assemblage vary with geologic age? So, is there a statistically significant difference between your Danian assemblage and your Maastrichtian assemblage? And we used a Pearson's chi-squared test with a simulated p-value of 2,000 replicants. I wasn't, for some reason, able to get just a regular chi-squared test to run, so I had to use the simulated value. If someone knows more about R and can tell me why that is, that'd be great if you could help me figure out what's going on there. But either way, with the data that we have, it pulled up a statistically significant result, which means that we reject the null hypothesis, and the assemblage is in fact statistically significantly different across the boundary. For the second question, we want to know, does the latitude range change across the boundary? Again, to a statistically significant result. We can sort of see this graphically, but let's test it statistically. And we did a Welch 2-sample t-test, and I was able to get a statistically significant result, which means that we can reject the null hypothesis once again, and the latitudinal range does change across the boundary to a statistically significant result. And that's whether you are looking at all the formations or just Hell Creek Tulloch. Cool? Okay. Okay, and then finally, do different genera live at different latitudes? So this was interesting because I think it was a Lyson paper that was saying that Plastomenace tends to be at lower latitudes, while Aspideratoides tends to be at higher altitudes. Weirdly enough, I actually saw the converse of that. We pull this down here. So here's Plastomenace, and then Aspideratoides is over here. And it's a little bit harder to see in this particular chart, but generally speaking, Plastomenace is just a little bit consistently higher latitude than Aspideratoides. So it's the opposite of what we saw with Dr. Lyson's work. That being said, I still got a p-value of 0.01, which is statistically significant. And so it would be fair to say that Plastomenace does in fact live at so we did two different tests. One of them was, does Plastomenace live at a higher latitude? And the answer is yes, it does. And then the next question was, do all the genera live at the same latitude? Which of course they don't, they live at different latitudes. And so we were able to, again, reject the null hypothesis. These genera are living at different latitudes to a statistically significant extent. Again, we can see this graphically, but it's good to just run the statistical tests just to be certain. So with that being said, here's some conclusions from the data. The vast majority of KPG Pan-Trionychids do make it through the end Cretaceous extinction event. Generic identification of fragmentary specimens is possible for most taxa, but differentiation among some closely related taxa, especially some of those plastomenids, can be really challenging. Lithofacies changes at the KPG boundary are incredibly impactful on the data, and so that both applies to the latitudinal distribution of these formations, but also the lithofacies, like the actual rock distributions of these data. So, for example, Compsomnes really likes ponds, and so it's possible that one of the reasons why they become so abundant in the Tulloch Formation is because it's a more heavily ponded formation as opposed to the Maastrichtian. I personally think that that's not necessarily lining up with the mudstone occurrence data that Dr. Lyson is saying that it is, but one of the future directions that we need to do is to go through each and every specimen and code lithofacies to test that empirically. Anyway, moving on. Danian specimens are consistently found at lower and more variable altitudes after the extinction event, even when controlling for geographical differences in formation exposure. The latitudinal changes across the boundary are statistically significant. And then despite the presence of both Danian and Maastrichtian facies, the relative abundance of Pan-Trionychid taxa does change to a statistically significant degree. Future directions, like I said, field notes containing the lithological context of in situ specimens need to be manually coded in order to better compare specimens to different formations. So basically, you know, turtle found in a mudstone, turtle found in a mudstone, as opposed to turtle found in the mudstone-dominated Hell Creek Formation and the sandstone-dominated Tulloch Formation, just as an example. We need better osteohistological sampling. So about 10% of the specimens that were identifiable in this data set are actually sectionable. So they have minimal sun bleaching, minimal superficial cracking, and a decent lateral extent that where they can be placed into the shell with high confidence. The other 90% of these specimens are just chunky, you know, gravel-sized pieces of turtle beds that are not good for histological sectioning. But that's my big headache right now, is talking with these 8 different museums and seeing which specimens are going to be amenable to sectioning and which ones are not. And then finally, once I can get a hold of these specimens, I would love to do some quantification of shell ornamentation morphology using Dirichlet normal energy, or DNE, relief index, and orientation patch count rotation, or OPCR. So Pamphilia et al. 2022 just did an excellent study where they're basically making 3D scans of the ornamentation and then quantifying them using these 3 methods, and then saying, okay, are these statistically significant differences between modern specimens? So by that notion, we should then be able to do the exact same thing with these fossil turtle bits, and quantify the external morphology of that ornamentation, run it through these programs, and see if what we're sort of qualitatively seeing, which is that some specimens are very clear and easy to identify, while others, especially those plastomenids, all kind of blur together. That should be measurable. And then from that point, if it is really good data, then you should be able to sort of automate the identification of these specimens just based on their 3D scans of their morphology, as opposed to the somewhat currently subjective process, which is just me, manually identifying these specimens, which works but is not ideal. So with that, I would like to thank all these wonderful folks at various museums for helping me get this data and just letting me see their collections and visit their museums. They've all been absolutely wonderful hosts. And I'd also like to thank David Kay for his help with getting some R coding done, and Haley O'Brien with her course lectures on how to navigate the various paleo statistical quagmires that one can find themselves in. Funding from this comes from the Vertebrate Paleontology Collection Study Grant at the University of Washington Burke Museum and the Natural History Museum of Los Angeles County Research and Collection Student Collection Study Awards, again from the Los Angeles County Museum. Yeah, I'd like to thank Holly Woodward Ballard, my advisor, Jack Horner, Jasmine Krogan, Tyler Lyson, Pat Holroyd, David Kay, Haley O'Brien, and of course, our Programming 101 on YouTube for helping me get all that code running. And here's my citations. I'm not going to read through all those. This is just the quick, like 10-minute summary. If you would like to get a actually good summary of all this, please come and see me at the in-person poster session for Research Week. I look forward to seeing all you bright and beautiful faces there. It's going to be great. We're going to have a great time. Yeah, go science, go turtles. Woo!